So I'm Robert, this is Rokesh. What we're going to do today is go through TensorFlow, obviously, at some point. We're going to start off with a little bit of background, why machine learning, why now, and also some of the steps that we need to be able to actually run machine learning in production. And then we're going to go through some examples. We're going to do some demoing in the second half of the session where we're actually going to look at how we can take our model and actually deploy it and train it and make predictions. So we're very much interested in what it takes to get machine learning into production. So I've got a clicker somewhere, actually. Where's that? Okay, there we go. Thank you. So machine learning at Google. I don't know how many of you are familiar with Google. Most people know Google as a search company, as an advertising company, we're getting more and more of a name now as a cloud company. We're working very hard to build up that name. But this photo best describes what happens at Google. I would say that 50% of the people that work at Google, well, more than 50% are engineers, and most of those engineers are busy with actually making sure that this happens, that we have data infrastructure across the planet. It's a big part of the story I'm going to tell you, so we're going to start off with it. This, just to give you kind of an idea, this is our network globally, and these are the data centers that we use for cloud. Why am I telling you this? Well, our experience at Google is basically if you want to be able to do machine learning, if you want to do something, let's say, intelligent with your data, well, you need to have access to your data, the data needs to live somewhere, so it all really kind of starts off at the infrastructure level. So before we can get anything into production, we need to make sure that all of this is in order. And we will look at one of the challenges here today before we go on to the machine learning component. It's basically, very shortly, just how we process data to actually get it into a place where we can actually start doing something with it. So I like this slide because when you're trying to do anything with data or machine learning, if you're not really thinking about, from the ground up, how you're going to put this stuff together, you're going to end up in a situation on the left. And that we've had a lot of experience in the company of actually learning what it takes to be able to build stuff up. And TensorFlow is actually part of that story. So Google Cloud, that's our cloud platform. We will talk about what we do with TensorFlow there in a moment. But Google Cloud, basically our objective with Google Cloud is to give you an option to compute, let's say, in a different way rather than just in a different space. So for example, with TensorFlow or Kubernetes, what we're trying to do is make sure that we have open source platforms that you can use to develop your code, and then we will give you a space within the Google Cloud to actually run this via a managed service. So when you're actually running this in production, you don't need to worry about scaling up, you don't need to worry about let's say downtime, those kind of problems. You can really focus on the functionality of your application. This is a very brief introduction, and I'm moving through this part a little bit quickly so we can get onto the meat of it, but this is a very brief overview of what Google Cloud is. You can see some of our big focuses here are data analytics and machine learning. So today we're going to look at, and the demo we're going to look at, we'll be looking at deep neural network. TensorFlow is particularly good for creating deep neural networks. Can I have a quick hands up in the audience who's actually working on deep neural networks, who's actually done some stuff on deep neural networks? Of those people, have you done some stuff with TensorFlow already? So, okay, a few. Any other frameworks that you're using out there? Maybe MXNet? Anyone want to shout out a framework that they're using at the moment? Okay, the cognitive toolkit. Keras. Okay, Keras is. I'm glad you mentioned that one. Thank you. We'll come back to that in a little while. So I guess you've all seen this kind of like insurgence of machine learning in these last few years, and why now? Why is it happening now? Because a lot of these concepts have been around for quite a while. It's not that we just started, 5 years ago with machine learning and neural networks. Some of this stuff has been around since the 60s. I think that, and that's also why we're bringing this presentation today along with cloud, is that cloud is playing a very important part in this whole movement to actually do machine learning. If you think about what you need, the ingredients for good machine learning is obviously having good models, and we've seen in the last years that those models have been improved as well. Obviously, when you can start programming and start actually running more and more models, you have more opportunity to start improving those. You also need to be able to store large amounts of data, and you need to be able to process it. I don't know if anyone can identify this, this chip on the right. 10 points. Sorry? TPU. Good. We got a much better picture of it later. Something makes me quite happy. So in Google Cloud, we have two ways of actually tackling machine learning. One is with TensorFlow, and the other is our managed APIs. So with the managed APIs, what we're trying to do is, in this way, we want to democratize machine learning. So for, let's say, common problems, so think about things like OCR, think about speech. We're going to look at a demo in a moment with video. For things that we can actually, we can create this model, we can train it, and we can actually bring it to the market, and people can use it in an easy way. Let's say for a developer to actually use that, embed that in their application. It could be natural language processing, for example, or translation. We basically want to run that by creating, easy to use open APIs. But for the stuff where you're actually building your own models, our approach in this is to say, okay, let's have an open source framework. And we'll look in a moment about what TensorFlow is and what the ideas behind the architecture of TensorFlow are, so that you can actually take your model, go and train it wherever you want, or build it wherever you want, train it wherever you want, and then also place it wherever you want so you can do your predictions. And what we do in the cloud space is actually offer a managed service where you can actually take your TensorFlow models, and we'll be looking at that, to actually run those and train them in the cloud, and also make predictions. So I'm going to give a little demo of one of those APIs, and then I'll show you the architecture behind it as well. Of course, I went the wrong way.
Why did you move it?
1 second. The demo effect, before the demo's even started. Wonderful. This is one of those new Macs. I've been giving them a hard time about it all day. So I will continue with the theme now. So here's an application that a couple of colleagues of ours put together to actually use our video API, so we can make videos searchable. So in this example here, I'm going to search for dog, and it's going to give me all the videos that have dogs. So we're going to click through to this video. I'm going to search for dog here as well. There we go. And if I actually go to this point in the video, I should be able to see there's a dog. For the same way, if I go to this point in the video here, I should be able to see there's a cake. There we go. I can go on, but you get the idea. So what does it take to build an application like that? How long do you think it took to put this application together? Hours, days, months? That's definitely not the one we put the challenge on Kaggle. No. No, you've got to work really hard for that one. Sorry? Did we do tests on this one? The guys who put it together, it was from our DevRel. I'm not going to say they did a lot of testing, no. Couple of hours. Let's go back to the presentation. This is the architecture that's used. So, I mean, tests or not, yeah, of course you can write your tests if it's an application that's going into production for our demo purposes. But we're looking here what you can do with an open API. So, what can you do with one of our APIs for machine learning? So, basically, what we've done is we've uploaded videos onto cloud storage, so just an object storage. We have serverless functions there listening, so when a video arrives, it will fire off an API call and actually process that video and get back the metadata, which will consist of what's the content of that video, and it will also consist of things like the timestamp when you can find that. So with that metadata, we can then serve it up. We're using App Engine here, which is our platform as a service, to actually create a small web application, and we're tying this together with Elasticsearch, so you can actually search through those applications, search through those videos, sorry. So this is really an example of something you can put together, and obviously if you're going to build this for production, write your tests and everything else, but it's an example without actually having any knowledge of machine learning, what you could create by using one of these APIs. But the rest of this talk, we're going to look about what it takes to actually make those models yourself, or importantly, what it takes to actually get those models to production. So this is our interpretation about what the popular imagination of machine learning is. So lots of data, difficult maths, and magical results. And it's quite a bad interpretation of what happens with machine learning. It doesn't do a lot of justice to all the hard work that goes into it. Reality is this. Collecting data costs a lot of effort. Organizing that data costs a lot of effort. And before you can even think about creating a model, you need to really do those first two steps. Then we have the creation of the model. Then we have to think about where we're going to go and train that model, how we're going to make the data available, etc. And finally, at the end of that, we have something that we can deploy to actually make predictions. So this, we're going to come back to this a few times today, but this is an architecture of how we might actually tackle a problem where we want to actually create our own model and bring it to production. So there are two lines here that I ask you to look at, the top and the bottom. At the top, we're basically looking at what it takes to train, and at the bottom, we're looking at what it takes to actually serve. So there's a few things here worthy of note. So we're using the cloud ML service to both train our model, our TensorFlow model, and we're using it to make our predictions. We could have those predictions made from a mobile phone as well, and instead of going via an API call to actually get our prediction, we could actually deploy the model compiled to a telephone, for example, if you want to do something offline. But in this particular case, we're actually going to look at making that API call to get our result. On the top, we're going to be using Dataflow. We're going to examine what Dataflow is, let's say, a MapReduce-like framework, and it's basically for unified batch and streaming, and I'll come into that in a moment. And you'll see also at the bottom, we're also using Dataflow. And the idea here is that anything that you're going to do to be able to train your data and to extract those features and then actually make those predictions, you're probably going to need to do the same when you're actually making those predictions. So if you think about, okay, where's that data coming from? What things do I need to do to extract the necessary features out to actually make that request? So wouldn't it be good to have some kind of framework where, when I'm working in perhaps batch mode or in streaming mode, I could actually use the same pipeline? So we'll look first at the collecting and organizing of data. So I'm just going to take an example of one of the difficult problems we have when it comes to actually collecting data and how we might solve that. So this diagram here is actually, let me ask people to put their hands out if you're already working with streaming data. So if you're working with real-time data. And put your hands up if you're doing stuff with batch. So now, put your hands up if you're happy with how you're processing data, and put your hands up if you're not happy with how you're processing data. So I've got a few hands on the not happy. Most of the time when I ask people about batch, they're quite happy, because when you're processing batch, everything's already laid out for you. So basically, your data set is complete. You know exactly what the whole entire population is there. You know what's going on. You don't have to wait for things to arrive. The things don't come in the wrong order or whatever. You can process it. It's quite comfortable to process. When you move that into a streaming, let's say, space, the problem is you don't know when your data is going to arrive. You don't know if that data is coming in the right order. You don't know if you're missing data. So how are you actually going to tackle those things before you can start processing it? So in this example here, what we're going to look at is processing time and event time. And along the bottom, event time is basically something happens now. And on the processing time is when we receive it and we decide to do something. So all those little dots up in the top there are kind of difficult for us because they all came, much later than they occurred. So how are we going to deal with those? So this is something we'd normally explain in like 10 or 20 slides to kind of go through. I'm going to attempt to try and do it in one. If you look at the ideal watermark, that's that dashed line. So this is where event time and processing time happen at the same moment. And if you look at the scores now, I should explain that. So let's imagine that this data is coming from someone playing a game, and we're looking at one person playing a game. And basically, every time they get some points, we're sending that to our server, and then we want to process that. So the first thing that we do here is create a heuristic watermark. The heuristic watermark is in green, and then we chop this into windows that we want to process. And those windows can be fixed time, they can be sliding, they can be sessions, depends what you're dealing with. In this particular example, we've got fixed time windows. As soon as those windows close, let's say that's the furthest right point of the watermark as you come to the end of the window, you can basically do something with your data. So in the first window, for example, as soon as we get that window closes, we can say we've got a score of 5, second window closes, and so on. What Apache Beam allows you to do is to take that idea of windowing and also take it further in the idea of triggering for things that happened too late or too early. So for example, those 9 points that we scored there, it actually happened at 2:02, but we didn't process it until 2:08. So what are you going to do in that particular moment? And in this case, what we're going to do is actually accumulate the data in that pane and then add it up to get the complete result. You can also discard it. It really depends on your use case. But what we want to show here is Apache Beam is an open source framework that we can use, again, with a managed service, data flow, to actually take our data and collect our data and then do some kind of MapReduce-like processing to actually have that data sorted so we can actually do our machine learning with later. I just wanted to look at one of the particular challenges. And these things typically take up a lot more time than people expect. You know, people want to get busy with the actual machine learning part. And in our experience, the actual focusing on collection of data and processing of data takes a considerable amount of effort. So now we're going to move on to the second part of the chain, which is the actual creating of the model and then using it. How am I doing for time?
Oh, good.
Good?
Yep.
Okay, cool. Let's come back to the pattern again. And now we're going to move on to TensorFlow. So to start with, this is a very brief history of TensorFlow. I'm not going to read it all up, but what I'm going to tell you about TensorFlow is a bit of the reason why we created it. So when we were trying in our own company to actually, we had researchers working on machine learning problems. They would come up with a great model, a great solution, and then we would have to take that to production. And then there was this big effort to actually take what we'd done in the research and then bring it into production. So we needed to make sure that we had a framework, a project that we could actually take the stuff that we were doing in the research space and the training space and bring that all the way to production and actually the prediction space. So that was one of the key ideas behind TensorFlow. Another key idea about TensorFlow was to actually democratize it, so to make sure that we open this up and get as much collaboration and contribution from the community as a whole. In that way, you know, you start to see things grow and you know, ideas improve and this kind of stuff. So TensorFlow. On the architecture side, to actually take it from, let's say, a space where you're actually playing with a model for the first time to a space where you're training that model to a place where you're going to actually make those predictions, you think about what kind of architecture you want to use behind that. So in the one case, you might want to do that on your laptop. So you're using a Jupyter notebook or something, working on your laptop, and you're trying to play around with a model for the first time. But as soon as you've done that, you might say, well, actually, this looks interesting. Let's start training it with some data, and suddenly your laptop's not good enough anymore. So you want to run that on a cluster, or you want to take advantage of GPUs or TPUs, which we'll look at as well. Once you've done that and you've trained your model, you want to serve it somewhere, so you want to deploy it somewhere, and you want to be able to make predictions with it. So that same framework should be able, again, to run it in a space where you can make predictions, let's say from a cloud platform in a distributed fashion, but it should also be able to deploy to a small device like a Raspberry Pi or a telephone. So you can actually use that work that you've made to actually do something useful with it. So those ideas was like let's say in the background or of how we were going to actually create TensorFlow. So a few things about TensorFlow itself. It's another data flow system, so this should look all quite obvious to most people. It's a case of nodes interconnected that are going to perform certain functions. That graph of nodes, all of the edges are actually n-dimensional arrays or tensors, hence the name TensorFlow. What's a tensor? A tensor is a multi-dimensional array. Why is that useful? Well, if you think about something like a convolutional network, one of the things that you want to do there is retain some shape of data as you go through from one node to another. So you might, in this particular case, if you were just dealing with a grayscale image, you might just have one channel, so a matrix. If you're going to deal with a color image, you might have 3 channels. And depending on what kind of data you're processing, this could grow quite considerably. And if you weren't able to actually transport that data between the one node to the next node and keep its shape, you wouldn't be able to do things like convolutional sampling. Or you'd have to do a hell of a lot of work to actually go and put all that back together again if you were trying to move that stuff across in arrays, for example. Another thing is having state. So when we're actually making this process in something like a BIOS, we need to go up and update, and we need to retain that state. So there's something else that TensorFlow takes care of. And the last part of the TensorFlow architecture is that it's distributed. So we can actually run some of those operations on some of those nodes on different machines or different chips. So this is a really kind of high-level overview of the architecture behind TensorFlow itself. TensorFlow is written in C++. We have APIs in C++ and Python. And Python is obviously the most popular one. This gives you an example, this doesn't give you an example. This shows you the architecture of how we actually use TensorFlow. So that part in orange is what we just looked at. And we're going to concentrate now on the Python front end. So there are a number of layers that you can work in here. We already mentioned Keras. Keras is at the same kind of level as our estimators. So in the layers, you can go in there, you can create all kinds of networks and whatever you want to. But if you're working in that level, you need to think about how you're going to distribute it as well. So how are you going to parallelize that work? So that becomes, for bigger models, quite complicated quite quickly. If you move up a layer to the estimators, so we have already some common estimators, like things like LSTM cells or convolutional, but we also have the ability to create a custom estimator. And if you use a custom estimator, then you don't need to have to worry about how you're going to actually distribute this or parallelize your network when it comes to actually training it. Keras operates at that same kind of level. And above that, we have, which is quite new, is canned estimators. And these are basically fully fledged estimators, which you can basically use out of the box for a particular, let's say, a regression or a classification problem. And we will have more and more of those, but they can be for very common problems, like I want to just run a regression on this. I don't want to do all the work. This is my data. This is what it looks like. You just have to map out the shape, and then you can start using those. So going back to the TPU again, so one of the great things that we can offer in this space is to go beyond a GPU. So a TPU, these things are running at, I think it's 180 teraflops per chip. So if you're really going to start to train your models at scale, the first generation of TPUs we were only using for inference, and the second generation, they're available for training and for inference in the cloud. So you could actually take your TensorFlow model that maybe you're running on your own server and say, actually, I need some more power for this. And then we could actually look at using TPUs in a cloud space. To give you some example, because there's numbers, what does 180 teraflops look like? To give you an example, some of our translation models that we were running would typically take us a few days to train. And now with the aid of TPUs, we can do that in hours. So it's a real kind of game changer at that level. And with that, we're going to move on to the demo.
Yeah, so what I'm going to show you is indeed coding, right? We're all developers, if I'm not mistaken, right? So, by the way, just to give you an idea, who was at I.O. this year? Google I.O.? Nobody. That's unfortunate, because if you see this TPU, it's really this big and this high. And it's a processor, right? Imagine that compute power. Okay, what we're going to do now is, what I'm going to show you is how TensorFlow can be used in a best practice situation, so with what we call the Google Cloud ML engine. And what we're going to do is we're going to more or less develop a model, we train it, and we test it. And testing, not like the context like unit test, but see if a prediction works, right? So it's time for some live stuff. Let's see, next slide. So what I'm going to do today is I'm going to focus on the data that is available in the United States Census income data set. That's about 32,000 rows in CSV format. And yeah, and it's this kind of data set that you have here. And what we're going to do is how you can use it for yourself. Imagine any data set, how you can use it for yourself, and yeah, start using TensorFlow in a very nice way that allows you to go to production quite fast.
There's a little mistake on that slide. It should not say convolutional layer. That's a copy-paste. In case that confuses anyone.
So just to give you an idea, this is the data set that you see here. So it's a bit big, but that is for you guys, so such that it's readable. But actually, we try to classify if a certain person can be classified as less than 50K per year or higher, or more than 50K per year. And that's what we try to do here. So this is the data set that we're going to use. And just to go back, so we present again. Yes. So what we normally do, and I think that is advisable for everybody, is instead of start coding in Visual Studio Code or VI or Emacs, whatever, you can start using Cloud Data Lab. Data Lab is nothing else than a Jupyter Notebook. Who's familiar with Jupyter Notebooks? Okay, cool. So for the people who aren't, it's in fact an interactive Python page where you can document in Markdown most of the time, and in Python code and live, and change your code and see the changes live happening. what I'm going to show you now is that this is immediately available in the Google Cloud Console. So Google Cloud Console is the environment where you can start up your services. Let me see. Where is it? Here. Is it readable? Yeah, more or less. So what you can do here is here on the top, there's an Activate Cloud shell. And in fact, what it does, it creates a small, how do you say it, a Linux instance where you can fire commands. And now it's provisioning. And if it's there, I can start the Data Lab instance and connect to it. So yes, here I am. So I have a command line now in my browser. I say Data Lab. Oh. Connect Data Lab for ML engine. That's a random name, by the way. I did press enter, right? Yep. So it's asking for verification. Bang. And here with go to port 8081. That's the port where it's hosted. I'll end up in a data lab situation where we can see the notebook itself. So now this is provisioned all in the cloud. I didn't install anything locally. I just can work. So just to give you an idea of the code that is involved. So we have tasks where you can, if it's a bit faster than this. Yep. So this is a Jupyter Notebook. Here you can see part of the code. I can fire it, but the whole idea is to show you that we have an environment where you can start, experimenting with your TensorFlow application, because it's not something you write immediately. It's something you iterate and you test and you try it out. And the Jupyter Notebook is something that you can use for that. So just to give you a little bit idea of what, in fact, an estimator could be like. This is an example, code sample here. Here you make a deep neural network with some specific classifier style with a couple of parameters, and that's it. And here what we're creating is, we're creating apparently 100 hidden units, followed by 70, followed by 50, followed by 25. That's quite deep already. So imagine that you have to program this. This is all tangled together, the fully connected network, by just this statement. So that's quite nice, and productivity-wise, also a very good thing to do. So let's go back. Then the next step is, okay, how do I train my application, the code that you just saw? How do you train it using best practices and using the Google Cloud machine learning engine? So we explicitly put it like this. So you have a situation where you say, local training, so that means on my machine only. We have a part, and there's a reason why we set it these environment entries, like the $train data and the $eval data. The reason why we did that is for flexibility, and I'll show you in a bit also what it's all about. So just one statement, and I can show it live. So to just show you that we're replacing the train data with a dynamic value of a local file system on my system. And then if I say run, sorry. So I'm actually at this moment running the code, and I'm going to show you a bit more. So you see here, this is also very interesting. So you see here warnings. They're not errors. They're actually giving you a signal that you're using a default TensorFlow implementation that is built for you already. But the good part is TensorFlow is open source. You can download it. You can compile it such that all these warnings go away. Yep. And the good part is it will be faster in runtime in the end, because it's tuned for your system. At this moment, apparently, I'm missing a couple of flags on my system. And as mentioned, you can say there's another thing that's coming up that's called TensorBoard. And here in the middle somewhere, here, you see a message, yeah, use TensorBoard to do the log there in the output. So what does it mean? What is it in the end? So TensorBoard, I'm going to start it up. TensorBoard is nothing else than a small Python application which is packaged with TensorFlow altogether. And it allows, let's see, it's open already. We're on port 66. So I'm copying this piece of code. Go back to my browser instance. Where is it? Here. And this is actually quite interesting. So now I have a tool, TensorBoard, which allows me to give me more insight in what's happening actually with my application. What's the accuracy? Accuracy is one of the important terms in machine learning. If it's high enough, you'll get a better score in the end, and it's more real-life situation. So you get some graphs here, and at this moment, it's still trying to improve a little bit, but it's not that good. And another thing, but these are some of the ways to, start investigating your code and start understanding what's happening and if it's giving a better result. Another thing that is quite important is that, as Robert mentioned, it's a graph that you're trying to compute in the end. So a moment ago, we talked about estimators, right? So estimator is like this one statement that we had as a deep neural network that's here. So this is, in fact, the graph of execution. So if you click on it, you get a much better feel of what's happening in the graph. So this is indeed a hidden layer on layer, etc., and then you get really fully connected, quite big network, and that's something you get quite fast. So the good part is you can follow the flow, you can see if the network is behaving like you want, and you can also start thinking, how should I tune it? Right? So this is TensorBoard. This is something you also get for free in the whole thing. So what I just did, I trained it locally, and with the output created, I can with TensorBoard I can look into it. But of course, we want to have more speed. We want to have more output or better output. So what we can do also is with just one flag, make it a distributed version. So what it's going to do, it's going to try to figure out, okay, what CPUs do I have available and what can I use or what GPUs, etc. Right? With just one flag, not changing the application. I'm also not changing the train data, etc. It's all on my local system. So the next step after this is, okay, now it's interesting. Now I realized I could do it locally and my data set is growing. So another thing that I can do is I can start running this thing in the cloud of Google. So Google Cloud ML Engine has a concept called jobs. And in fact, everything that you have, so your TensorFlow application, with your parameters, with your data set, you can say, okay, here's my package, more or less, and execute it in the cloud. And what you get is that you're going to get finally the benefit of having cloud in the background supporting your calculations, which can be quite heavy depending on the on the size of your data. And also in this case, the train data and the eval data are not your local file system anymore, but it's your Google Cloud Storage location. So what we've done is we uploaded the files to that location and said, okay, from now on, because you're in a cloud environment, you want to have fast access and not network latency or whatsoever. Execute it over there. So what you're going to get is, if you do it a couple of times, let me see, here it is. Yep. Let me blow it a bit up. Yep. So what you see here is that you get an overview of the jobs that have been executed. So you can see the jobs that are nothing else than just a REST request that we're doing to the server. This is it. And in the end, it starts executing and it writes its output to the file system of the Google Cloud Storage. Because, and there's a reason why. You want to go not single training mode, of course. There's a way to do this actually in a distributed way also. And distributed computing is very interesting in the cloud because you can decide quite easily to start upgrading to certain scales that we know. So this is a default scale of just saying, okay, this is a situation where I have less parameters, or not a few parameters, and I have a deep neural network. That's it. So you can start using the standard one distributed. We also have other configurations. So with just one flag, you can also say, okay, start using GPUs, and actually also start using TPUs if you want to. So the interesting result is that might be some noise cancellation situation here.
Is that the 10 minutes to go one?
Yeah, I think that's the cue. So what you see here is that I did a Census 1, Census 2 single, and what you also see is that it took about 10 to 12 minutes. But with just one flag, I made it possible to run the distributed version of the same code in 6 minutes. So imagine the time savings that you have. And we were talking about a case where Google Translate took like a week to train, the version that you guys are using also. But with TPUs, you could do it in a couple of hours.
Yeah, it's really reducing like days to hours in that scale.
And that's just by flagging it. So you experiment, you play with it, and you see the output. So then another step is, okay, finally I have a distributed model trained.
Oh, you've gone.
Yeah.
Yeah, you've gone to the so it was just, yeah, no, go back down to the next one, the way you were, so on the pod.
Oh, this one. Yeah.
One more.
Sorry?
One more. So these are the pods of TPUs that we actually can offer up in the cloud. So they're 11.5 petaflops per pod. So if you're really going to train something at scale, and this is the powerful thing about TensorFlow is that you can just take what you've created and move it onto these different architectures just by changing those flags that Rokesh just showed you.
So okay, so now we have a trained model. So what do you want to do with it? Put it in production, right? That should be easy as you guys know how to do Java web application development or Node.js or whatever. It should be easy. So what we said is, okay, first of all, you create a model in your cloud environment. That's the first statement that you have, create model. With model name can be anything. And a region, so the US region. All the regions, by the way, have to do with latency, but that's a different story. We can talk about it later on. And then, in fact, what you do is you create a version of your model. Because you might be tuning it, right? You might be playing around with it, might be changing the format, you might be changing the network. So in the end, it's possible for you to have a trained model deployed in the cloud that you can start using for execution. So how does it look like? So here I have a model. It's a census model, and it has a specific version. So you won't have, I don't think you will see a version, a model without a version. There's always a version behind it. And in the end, it's deployed, it's available, and you can start using it. So what does it mean to use, right? So what we said is, now the interesting part is, so now I have a model, so I showed you how to go from code, data lab, to training locally, to training in the cloud, to go to a deployed version. The next step is to test the prediction. And the nice part is, it's all REST-based, so if you have an application that runs any other language than Python, no problem, could even be .NET, you have a REST endpoint, call it, get an answer back, start showing it to people or use it for your calculations or whatsoever. But in this case, I'm going to show you also live that, let me close this one, that if you, I'm not sure if it's visible. Oh. Doesn't matter. Let's say run test predict, and test predict is, so I'm going to fire it off. So now it's in fact sending a test file with just one entry in this case, one entry of a person in the US with those fields in there, and it's sending it to the Google Cloud to make a prediction and also specify it with which version number. So you can play with it, and in a couple of seconds, there it is. It could predict that it's in the class 0, so if you look at the code, it will try to categorize the output. Instead of saying larger than 50K or smaller than 50K, it will try to create numbers for it, 0 and 1. And with a probability of quite high, 0.99%, it says that it's in class 0 and it's less than 50K. So I guess that's my demo, right?
Yeah. So we can just move back to architecture. How much time we got left on the clock?
Yep.
6 minutes, so we'll just do this very quickly. So as Rokesh just showed you, we've basically gone through this whole pipeline. At the beginning, we looked at how we could use something like Dataflow to actually process data, to do that feature engineering, and we just looked at how we can use CloudML. The really important part that I just want to emphasize in that CloudML, we're making a model in TensorFlow, but we're using the CloudML API to both run that and train that model both locally and in the cloud and make the predictions. So we're actually using the CloudML API. That really makes that hurdle from going from our own local instance to going to a cloud space or distributed very easy. And again, if you want to do something on the distributed scale, and you don't want to do all that plumbing, because if you go down into those layers, then you're going to do a lot more plumbing. Then you use the estimators. And if you have your own, if you don't find an estimator that fits what you want to use, then you create a custom estimator. There is a code example. There is a whole tutorial which kind of supports this as well, so we can put those on the slides and share that out as well. So if you want to actually go through this example, and this example is not the best example to learn what does a neural network look like and how do I make a neural network, but this example really shows you how do I actually start getting a neural network from my local machine to training it in a space to be able to predict with it as well. And I think we're good there.